All right, so this is Unit 8 of AP Physics C, Electrostatics, which we will be reviewing for the AP exam. So the most fundamental, or I guess the most basic idea of electricity boils down to the idea of charge. Charge, when you hear the word charge, you probably like associate it with like electricity, just with connotation. But charge at the most fundamental level is just a property of matter, right? In the same way that mass is a property of matter. And what we've realized is that in this universe, objects are really made up of two types of charges: positive charge and negative charge. So if you think about an atom, like if I were to just draw, I guess an atom right here, they have positive particle, or they're made up of protons, which have a positive charge, and they're made up of, and I probably drew this wrong, but they're made up of protons, which have positive charge, electrons, which have negative charge, and then neutrons, which have no charge. So when you think about an atom, like those subatomic particles have that property of charge, and what we found is that if you take a positive and a negative, and positive and negative, they're just names, right? We could have named these two charges like trombone and ravioli, right? Like the names, they're just names that we've given them. But what we've found is that when you have two of the opposite charge, right? If you have a proton and an electron, or just a positive charge and a negative charge, they will attract each other. So there will be this attractive force akin to the gravitational force, right? Like that, or like similar to the gravitational force, that is this attractive force as a result of mass. But now we're seeing forces due to charge, this other property. What's different from gravity is that if you take similar charges now, right? If you take a positive and a positive, they will repel, right? If you take a negative and a negative, they will repel, which we don't see this with gravity, right? And I'm giving this a subscript E for the electric force, because we call this force due to the electric charges, like the electric force or the electrostatic force. And this repulsive force we don't see with gravity, right? We don't see mass repelling each other. Now with gravity, we have an equation that will allow us to kind of figure out what the gravitational force is due to like two masses. And for electrostatics, we have an equation that does quite the same thing for charge. So there's this electric force. How do I figure out how much force there is? Well, I could say that the electric force is equal to K Q1 Q2 over D squared. So breaking this down, the electric force is equal to K, which is a constant, times Q1, which is a charge of one of the charged particles, times Q2, charge of the other, over D squared. They're the square of the distance of separation. Now this constant K, it's called Coulomb's constant, right? It's equal to 9 times 10 to the 9th, and then whatever units. So I think the units would be Newton meters squared over Coulomb squared, right? So that everything cancels out to newtons. This constant is also equal to another kind of constant. This is also equal to 1 over 4 pi epsilon naught. I think epsilon naught is it's either the permeability or the permittivity. I keep forgetting. It has a name to it, and we're going to see why this constant also exists later on in this video. But this is the electric force equation. So if I know, I know that if this was a proton and this was an electron, I know that for both of them, they have a charge of 1.6 times 10 to the negative 19th Coulomb, right? This is a really small amount of charge, right? This is 10 to the negative 19th. Now, for the electron, right, it would, so if this is a proton, then it would be positive. If this was an electron, it would be negative. So when you plug in your numbers, you would find that, well, hey, positive times a negative, that would result in a negative force. That negative force just tells us that the force itself is attractive. And I think if you get the vector form of this equation, which will actually spit out, like this is really the magnitude, right? So the negative doesn't even matter. But if you have the vector form of the equation, then that negative, I think, helps you determine, like, is the force pointing towards your source or like towards the, the proton or away, right? Like, that's what the negative's there for. But you don't have to really worry about it too much. Just note that a negative amount of coulombs, which hopefully I didn't really mention this, coulomb is the unit of charge. That means it's like a negatively charged object. So that's how we kind of determine like whether charge is positive or negative, like mathematically at least. So that is charge. Now, if you think about a neutron, right? So if you had a neutron, you would probably think that, a neutron will not get attracted at all to either. And that's probably right. I mean, maybe there are some quantum effects going on. But I mean, classically, if you just look at this as like a AP Physics C students, yeah, neutron has zero charge, so your Fe just spits out a zero. But let's say we have a rod, and this rod, we'll just say has a negative charge, all around it, and I put it near a neutral aluminum cylinder, right? So this is like if this is a cylinder, I guess maybe just to make it look more like a cylinder, I can draw it 3D. But we have a neutral aluminum cylinder. You might be thinking nothing's going to happen to the cylinder, right? If I take the rod near the cylinder, it's not going to move because my amazing Coulomb's law equation tells us that if my charge is zero, then the electric force has to be zero. But if you were to try this at home, right? If you were to charge a pipe or like a rod, and we'll talk about charging and how to do that and the different types. If you were to do this, the aluminum can will actually start rolling towards the rod. But why, right? There can't be any attractive force, but there is. Now, hey, we're made up of atoms, right? We're made up of molecules, and these atoms have a bunch of electrons and protons. And if you have something like aluminum is a conductor. So a conductor, if you get into the chemistry of it, there's probably, there's definitely a lot of chemistry in electricity and magnetism, but the basis of a conductor is that electrons are freely able to move around the material, right? Compared to an insulator, which it's bonded in such a way that you can't really have electrons freely move across the conductor. So this thing is made up of atoms. So I'm gonna draw like positives here, negatives here, positive, make it kind of random. But the idea is that we have a bunch of different charges, right? And I can make sure they're neutral. I think that's 6 negatives and I think 8. So I'll just add in like a couple more negatives. But there's pluses and minuses. But when I bring this rod over, hey, the electrons get repelled away, right? Like they're like, oh, I see these people who are just like me. Well, that's a really weird way to say it. But the point is they get repelled away, right? They see the electrons, there's that repulsive force, and electrons, they're able to freely move around. So what happens is all of these electrons, right? So if this is minus, 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 they all essentially go away to as far as possible from the rod, right? And now what happens is you have overall, right, the protons, first of all, protons don't move, right? I think it requires like a great amount of energy to move protons. You could ask a chemist about that, and you know, they made a whole 3-hour movie called Oppenheimer about it and destroyed a lot of cities using that. But yeah, protons don't move, but in general now there's much more positive charge. So a lot of, you know, a way that sometimes classrooms will draw it is like, oh, this is before, right? So before, and then this is after. So if I had my negatives here, they would kind of draw it like this, or other way, just pretend these are positive, right? Let's switch up the problem. But they'll draw it like this, where it's like, oh, the positives moved away to one side, negatives got closer. Well, in reality, what happened was the negatives moved closer, but the protons never changed. It's just now overall, there's more like positive on one side, right? There's less electrons on one side. That would lead to more positive. So that's like the nitty gritty of it. Like, I guess a more realistic model. I think if you draw what I just drew on an AP exam of like positive charge moving, like that's fine, and that's fine. And you've seen in this course that, yeah, positive charges move when they really don't. But point is, negatives move away. There's more positives. There's overall a more positive side. Let me draw this out. This side is now more positive. This side is more negative. Hey, Coulomb's law has that square inverse proportionality with distance. So if the positive side is closer to the negatives, right? If I were to just draw, like, I guess an FBD of this, there would be this electrostatic force due to the positives, and I just dropped my pen, but there's now a net electrostatic force of repulsion due to the negative charges, but positives are closer, so it would result in a greater force, right? Smaller d, greater force. So it's gonna, there's overall the net force. So the F net would be overall towards the rod. And you can think this through. It doesn't matter whether this is a positive rod. You could draw your diagram as I was kind of showing over here. You would find the same result, that neutral objects, not necessarily neutrons or particles with zero charge at all, but neutral objects like aluminum cans or whatever, they would get attracted to a a positive or a negatively charged object. And with inductors, it's a little bit different, right? Because with inductors, if you had a balloon, right? If you had a balloon, inductors are kind of, and let's say we have like a wall here, right? If, let's say I charge, and one quick note I should mention, if I have, let's say this is an aluminum can, right? Like a metal ball. So metal. If I were to add charge, actually, we'll talk about, you know what, yeah, we'll talk about this with types of charging. So types of charging, right? We talked about having this charged negative rod, but how do I make an object charged? Well, there's three big ways, kind of two, I guess, but there's three big ways to really do it. First of all, there's charging by contact. So hey, let's say I have something that's already charged, and let's say, right, let's say I have something charged like a rod, or I have like a Van de Graaff generator, right, and I want to transfer some of the charge over. I can charge an object by doing this. So if I have like a bunch of negatives here, right, if I have a bunch of negatives on this rod, when I touch the metal ball here, because, right, metal is a conductor, allows for the flow of electrons, yeah, these electrons are going to transfer right over onto the metal. So afterwards, with the metal, you're going to have a bunch of negative charge. How will that charge be distributed? Well, it's going to be distributed all over kind of the I guess surface of the metal sphere. Even if it's not hollow, even if it's a solid metal sphere, all the positive charge will sit, sorry, negative charge in this case, will sit on the surface. And that kind of makes sense, right? Because all the excess electrons that I added to this metal sphere, or excess negative charge, whatever, um, I guess those are kind of interchangeable, but whatever. All the excess negative charge, they're all repelling each other, and they all want to get away from each other. So they're going to kind of try to maximize their distance away from each other by spreading out, right? If you had a bunch of, this is a weird example that I told my friend, but if you had like a bunch of stinky people in a room and each of those people also hate stinky people and hate the smell, well, they're going to like run away from each other and then just be like at the walls of the room, right? If you put them all in a room, they're just going to be banging on the walls and basically making a whole perimeter, right? They've surrounded the surface, or not surface, but kind of like the, what do you call it? Like I guess like the perimeter, right? Like all the negative charge, it just sits on like that perimeter or the surface of the sphere. Now, if this was, let's say I put some charge, right, with my metal rod, I put some charge onto a balloon. Well, a balloon is an inductor. Did I say inductor? I hope I said insulator in this video. I just thought of saying the word inductor, and now I just realized that I probably said inductor somewhere else. That's really bad, but not enough for me to make a new video, so we'll just roll with it. I'll just leave a note in the comments. Insulator. Okay, insulators. They, like I said, they're bonded in such a way that the electrons don't flow freely. So if I were to add electrons to the balloon, the electrons, they would jump over, but they would just sit kind of in one spot, right? Like they wouldn't spread out. They would stay in one spot because the electrons simply aren't able to move around. So that's, one thing to note there is, electrons and inductors, they don't, oh, that really sucks. I shouldn't have said inductor. Insulator. I really hope people are smart enough to be like, I'm in electrostatics, and this word is associated with the last unit of this course. So I think he made a mistake. Hopefully you guys caught my mistake. Point is, now if you had a neutral wall, this will actually still attract, right? If you've done this before, you can take a balloon and stick it up to a wall, and even though a wall is, I guess, an insulator, and a balloon is also an insulator, you still kind of get a polarization effect. And I forgot to describe this. This is what we call right here polarization. So, what happens is if these bonds, right? If these bonds right here, these molecules are like positive, negative, or, negative, positive, right? They're just randomly oriented. But these electrons, they cause them to shift, right? These bonds kind of flip over. So now the negative side ends up facing, positive side ends up facing the electrons, right? Because they're attracted. And that's what causes them. And then you get an overall force between them, a force of attraction, and that'll cause the balloon to stick up. So, that's charged by contact. Charging by friction, right? I forgot to mention this. Oh man, I'm making so many mistakes. For a rod, you can't really touch the balloon and get charge to jump over. I mean, maybe if the rod is like a conductor, but let's say you have a balloon and your hair, and you want the charge on your hair to jump over to the balloon, or vice versa. How do you want to go about doing that? Well, they're both insulators, so electrons are probably gonna have a hard time, really jumping over to one side or the other. So you just got to give it a rub, right? And we call that charging by friction. So that friction, you could there's I don't really understand the science behind how friction leads to that. Maybe, I don't know, causes energy, and or it gives the electron energy and that allows jumps. I don't know, to be honest. But what we do know is that friction will lead to like charges rubbing off on one another. So that's how you can charge an insulator kind of better, is with rubbing. But the third way is through induction. So right here is actually basically induction. What I've done is I haven't given this aluminum can a charge, right? I haven't given this aluminum can any charge, but I've induced an apparent charge where you think to yourself like, hey, this is negative, so this is being attracted to it. It has an induced positive charge. So that's induction by polarization, where your charge kind of like splits, or not splits, but it's like that electron flowing, right? Like the electrons get repelled away, so you have an overall positive charge on one side. Now, in order to really charge this thing, you gotta use you gotta do grounding. So grounding, you know, these negatives, they are kind of, you know, they are kind of wanting to get away from the negatives from the rod, right? Well, how nice would it be if they had like a little escape route to get away from the negative rod as far as possible? Well, hey, that's what a ground does. So I can take like a wire, or really any conductor, right? And I could connect it to a surface or an object that can basically act as an infinite like source of it's hard to explain really, I think, without potential, because I want to kind of bring in potential concepts here. But basically they're like it's like a deposit, it's like a free deposit of electrons, right? Electrons can go there as much as they like, or you can withdraw as many electrons, right? Like it's like how do I explain it? I should have brushed up a little bit more on like a good definition of a ground. But yeah, a ground basically is like an infinite amount of charge. So like the Earth is a ground, right? Because no matter how many electrons enter the Earth, it still remains essentially neutral, and more electrons could just keep going and going and going, compared to like a metal sphere. If you just had a bunch of electrons going in, eventually it gets kind of fully charged, and electrons would no longer be able to enter the sphere without getting repelled away. So that's basically what a ground is. And you can think of the Earth as a ground, right? The actual ground. And I forgot the little notation for ground. But so it just I don't know what the symbol is. But now these electrons have access to a ground, and that'll allow all of these electrons to just head over and take this path down the ground. So now you just have a bunch of positive charge on the conductor. So using a negative rod, I can actually give the aluminum a positive charge via grounding. So I just gave a pretty long lecture on just electrostatics, right? And like, you know, just some of the more conceptual things. Now let's talk about some of the more just mathy things. So there's this idea of the electric force, right? And one way we can kind of model the electric force, or kind of understand it, I guess, is like why there is an electric force in the first place, like why that exists, is we can think of something called the electric field. So, hey, I have this positive charge right here. Now, what I can kind of say is, well, on Earth we have like a gravitational field, right? So Earth is kind of creating this gravitational field. So if I think about Earth, right, if you're standing on Earth, you know, there's obviously gravity and stuff, and like Earth has a gravitational field. So any mass that I put, like if I put the moon, or if I put a rock, or if I put whatever object I want, right, these lines kind of tell us which way the gravitational field points, and by extension, which way the gravitational force points. So if I put a rock here, assuming it's not moving to begin with, it's going to begin accelerating this way, and well, it will accelerate this way regardless of its motion. But if assuming it starts at rest, it's going to start moving this way. Or if it's moving this way, right, it's going to start moving in a circular motion, in circular orbit, because this tells us which way that force points. So in a similar way, we can kind of model an electric field, and this electric field, by convention, points outside, or not outside, but points away from positive charges. And the electric field tells us the direction of the electric force on a positive charge, right? So if I put a positive charge right here, this kind of vector tells me that the electric force will point to the right of the page, right? And for negatives, you just flip that. So if I put a negative here, it's going to point to the left of the page. And you can use a common sense check, right? I know opposites attract, so if I put a negative here, I would assume the direction's flipped, because I know it has to attract to the positive charge. So the electric field is created by one charge and affects others. So the equation is really the electric field is equal to KQ. I should probably draw this bigger. So E is equal to KQ over D squared. So very similar to the force equation, except now, actually, I'll connect it back to the force equation in a second. Point is, this is the charge that creates the field. Creates field. And this is the, that's the charge that creates the field. If I place a stronger charge, that electric field will get stronger. Now, if you move farther away from that distance, the electric field gets weaker. I mean, who cares? But who cares about the electric field, right? Like, what's the deal? Well, the electric field can tell us essentially like a predictive force, right? So the electric field is proportional to the electric force, I guess, and it's like, if the electric field is increased at a certain point, right? So if I increase the electric field at this point, the charge that is affected by that, field will experience a greater force, right? So even if I don't know what that charge is, the electric field kind of serves as like this predictive value where it's like, if I know my electric field is stronger, I know my electric force is going to be stronger, regardless of the charge. And if I know the electric field at a certain point, well, that becomes real easy because now I know, depending on whatever charge I want, right? Whatever charge I put in that place, I can very easily just calculate the electric force. And yes, you could probably notice if you this is the electric field due to a point charge. So if you have 2 point charges, you can substitute that equation back in. And you just get the electrostatic force equation. But here's the deal. Objects that are charged are made up of many point charges. So if I have a rod, right? A rod, and let's say it has charge uniformly distributed. So, there's charge that kind of exists, right? Maybe it's a conductor. So the charge just kind of uniformly exists, like linearly, right? So this is like a thin rod. We don't have to worry about like it being a thick rod with like a bunch of charge in the middle or whatever. It has charges linearly distributed over this length, L, and I want to figure out, well, hey, what is the electric field? And let's say it has a charge Q. I want to figure out what is the electric field at a point like R away from one end. You might be tempted to use the electric field equation right here, but this is the electric field due to 1 point charge, and there's a bunch of different point charges. So if we imagine this being like the x-axis or whatever, you can imagine that there will be a small little dq right here, a small portion of the cylinder that will have a very small charge dq, and that small charge dq will create a small electric field dE. And it points towards the rod because negatives have electric charge pointing towards the rod. So in this case, we can see that along this x-axis, right? So if this was like our origin and this was like a distance x away from that point, well, the electric field will just equal, I'll maybe make this a little bit bigger. The electric field will equal k dq over x squared, right? Now, I know that the total charge is distributed proportional, like evenly across this length. So I know the charge per length is a constant at every single point. So I can say, well, Q over L, that total rate, like that total charge to length ratio, will equal dq over dx, right? Over that little change in x along this x-axis, right? So I know dq is really just q over L times dx when I separate it over. And you could probably see, yeah, we're gonna have to take an integral real soon. dE is gonna equal k. Now you can make a variable for this, right? Sometimes a problem will tell you, well, the linear charge density is lambda. This is what lambda is, right? Lambda is just that q over L. So we have q over L times dx over x squared. Now I can integrate to find the total electric field, right? Because that's what integration helps us with, right? It helps us find the total due to like small accumulations. So, you know, this is going to be a number, right? I'm not just taking an antiderivative, it's going to be a definite integral. So what are my bounds? Well, you would think maybe, well, I'm starting maybe at 0 and I'm integrating to the total length, and that's not a bad thought, but remember, we're looking at, if this is the x-axis and this is the origin right here, I'm starting at A, or R, I should say, R, and I'm integrating to R plus L, right? Because the closest possible charge, or closest possible dq, will be that distance R away, not a distance 0 away. So, you know, when I take this integral, I can pull out the kq over L stuff, so kq over L, right? Because that's all constants. And then I have 1 over, so if you think about fundamental theorem of calculus, first of all, to integrate dx over x squared, it would be negative 1 over x. And you're doing negative 1 over r plus L minus negative 1 over r. If you clear up the algebra, it just becomes 1 over r minus 1 over r plus L. And, you know, you can simplify this further, but this is just to show you how we can use the point charge equation to find electric fields due to objects. Now, a more complicated example would be if I had a rod, how can I find the charge a point P away? Now, like a point P away, like kind of like, not, I guess horizontally, I guess, I don't know, like not like to the side, but rather like, you can see the picture. You know what? I don't have to explain. Picture is 1,000 words. I need to find the electric field at point P. This is actually a much more complicated example. And if you go through your steps and, you know, you're not to integrate with thetas and stuff, it's a pretty hard integral. And, you know, I have a video on how to go about doing this using this equation, but there's a better, easier way, assuming you make some approximations. We first got to talk about electric flux. So electric flux, to put it simply, it's the amount of field lines going through a surface. So if I had a square, right, and I had maybe a positive charge, like right here, positive charge right there. Now that positive, no, let's not do a positive charge. Let's say I have a uniform electric field. And uniform electric fields you can actually create by having a sheet of charge by a sheet of opposite charge. The electric field would actually be uniform. throughout that sheet. So if I have a uniform electric field, there's going to be conceptually speaking, it's like the electric flux is the number of field lines passing through that surface. So it's like the number of field lines piercing through that surface. And that's conceptually, right? We're not literally counting, like when we're calculating, we're not literally counting number of field lines. Instead, we have the equation electric flux is equal to E, so the electric field, times the area times cosine theta. So cosine theta is the angle not between the surface and the electric like field line, right? It's not like this angle is 90 degrees. This angle is actually 0 degrees because we're measuring the angle of the normal vector. So if you think about the area, it's going to have like a perpendicular kind of direction, like a normal vector. So that normal vector and the area, or not area, sorry, electric field vector, if that angle is 0, right, you just get E times A, because cosine 0 is 1. As you increase theta, cosine theta decreases, so your electric flux decreases, which makes sense, right? As you start increasing that angle and making it like less aligned, then there's going to be less field lines going through that that sheet. So that's electric flux. It's useful because, well, if you don't have a constant electric field, you have to integrate, right? So you have to take an integral of E dot dA. And that dot is telling us it's a dot product between the area vector and the electric field vector, right? Now, there's this clever guy called Gauss, and he figured out that if you took this closed integral, right? And what this means is if you had a charge, right? A charge, and you had an imaginary surface surrounding that whole charge, right? This 3D surface encompassing that whole charge, and you were to calculate the electric flux across the entire, like, thing. Across the entire surface, right? If you were to take the integral and to find the total electric field, you would get Q enclosed over epsilon naught. And that's where epsilon naught kind of comes from. It's like, another constant. So if you don't know K, you can use epsilon naught, right? Instead of writing like 4 pi K or whatever. So that's kind of cool, right? And we call this Gauss's law, but why is that useful? Well, in a lot of cases, you can actually get symmetry, where in this case, this would be a pretty nasty integral to take, right? Because it's like the angle's changing, the distance is changing, the strength of the electric field is changing. But if you imagine, like, for a cylinder, right? If you imagine a cylinder, right? So a cylinder has electric fields. If you imagine this is my cylinder line of charge, there's like electric field kind of pointing radially outward, right? Hopefully that kind of makes sense. The electric field is pointing radially outward. Well, what I can do is I can actually, so if I do my cylinder, like my line of charge, like so, I can actually think of like an imaginary surface, which we call a Gaussian surface, which will it'll be such a shape that we can kind of use symmetry, right? The points along this entire surface, right? That entire 3D surface, the electric field is the same at all those points. And what that allows us to do is it just allows us to take the E out of the integral, right? The electric field would not vary with the area, in other words, right? Like it's not a varying value. It's a constant value for that entire surface. So I can say like E times the closed integral, I guess, dA is going to equal Q enclosed over epsilon naught. So if I know that Q enclosed, epsilon naught is a constant, I can just find out the electric field because I know that this integral, if I integrate all the dAs, that's just the surface area, right? The surface area of a sphere or cylinder would be, it would be, I have to kind of think about it. It would be, so if this is a length L, it would be 2 pi. So the main like like that cylindrical kind of portion would be 2 pi r L plus 2 pi r squared for the tops. But we're not worried about the tops, right? Because we know that there's generally not going to be any electric field coming that way. Now, in reality, yeah, that will happen, right? Heck, that's how we got this problem. But if L is really, really, really large, we can kind of ignore that. So, and that makes sense for this problem, right? If L becomes really, really, really long, then that's not even going to have an effect. So, therefore, I can say, well, E times 2 pi r L is then equal Q enclosed. That's just lambda times L over epsilon naught. The L is dropped, and I get E is going to equal lambda over 2 pi r epsilon naught. So that's just an example of Gauss's law, right? Gauss's law is kind of easy. You just got to know how to use it. This video is already long enough, so I'm not going to go over like every use case of Gauss's law. But someone has made a video on that, right? You can do practice, get comfortable with Gauss's law, and don't drop your pen while you're at it, and you will, be able to master electrostatics. That's electrostatics. I'll make a video on voltage. Good Lord, 41 minutes. I will make a video on like electric potential and voltage in the Unit 9 video because that, College Board associates that with a different unit. But yeah, thank you for watching.